Okay, welcome to Chapter 1, Introduction to Statistics in Biostatistics for the Biological and Health Sciences. In this section, we're going to talk about statistical and critical thinking. We'll talk about the context, source, and sampling method of data, voluntary response sample and implications for interpretation, statistical versus practical significance. Okay, so why do we do statistics? Well, this depends on how you define your population. If you want to measure something from all of the United States, if the United States is the population of interest, there's no way you're going to get a average height or average salary for the entire United States. The population is just too big. We don't even know how many people really are in the United States, so it's just not possible. So we use a sample to represent the population, and then we take a measure of that sample and use it to infer back to the population. But your sample needs to be representative. If our population is everyone in this class, that's definitely possible, and therefore I could take a measure, an average, say, of your quiz score, and that would be representative of the entire population if I've defined the population as just the class. I'll talk more about this in a second. Okay, so if your population is large, too large to know the information, we draw a representative sample, we take some sort of measure of that sample, and then we generalize back to the population and make inferences about it. That's why we do statistics. We use samples to make inferences about our population, and it's important to consider how that sample was formed. If it's through random sampling, if we randomly sample from a population, then we can say pretty sure that that is representative of the population. That's the best way we can do it. If it's not, then our findings may be biased or suspect, and I'll talk more about that in a minute. Statistical versus practical significance. And I'll talk a lot more about this later in the semester, but statistical significance occurs when you find a result that was very unlikely to occur because of mere chance. And practical significance implies that although a finding may be statistically significant, it may not be practically significant to pursue it. For example, on page 8 of example 3 there in the book, there is a gender choice drug being tested, which can allow you to select the sex of your child. It only improves the chances of selecting the gender that you want by 2%. So you go from 50-50, which is naturally occurring in the United States or in the human population for gender of a child, to now 52-48%. Statistically, it's significant, the results of the drug, but practically it only gives you a 2% increase, and therefore it's not practically significant to pursue the development of that drug. All right, so we have different types of data. We're going to talk about parameter and statistic, quantitative and categorical, discrete and continuous data, and determine whether basic statistical calculations are appropriate for a data set. Okay, so you know in statistics you're going to see some Greek. And we use Greek letters in statistics to represent a parameter, which is a numerical characteristic of a population. Conveniently, they both start with the letter P to help you remember. Parameter is to population as statistic is to sample, which we'll get in the next slide. And also, we're really familiar with the Greek letter for pi, right, the 3.14. But this is also just the Greek letter pi. So I could rewrite parameter with the pi and population with the pi to remind you that when you see Greek letters, we're talking about parameters, which are numerical characteristics of a population. This is a lowercase sigma squared, which is the variance, and a sigma is the standard deviation. I don't expect you to remember that, but I just want you to see these Greek letters. And we'll talk more about this in the future. When you don't see Greek, when you see the Latin letters, we're talking about statistics, which are a measure of a sample. So again, parameter is to population as statistic is to sample. We use the Latin alphabet, and you'll see that M is equal to the mean, and now S squared is the variance, and S is equal to standard deviation. All right, we have quantitative data, numbers that represent counts or measurements such as weight, height, blood pressure, etc. Qualitative data are interested in the meaning, not the frequency of a particular phenomenon. And we're not going to cover qualitative data in this class, but when you go and ask questions of people who've experienced a phenomenon and you have them tell about their experiences, that's qualitative data. Quantitative data is what we'll talk about in here, numbers that represent counts or measurement. All right, so when we talk about categorical data, it's also called nominal, and you can see the Latin root nom in the word nominal, meaning name. If you know Spanish, the word nombre means name. If you know French, the word nom means name. These are variables that label. We use numbers to code these data, so male is equal to 1 and female is equal to 2 if the variable is gender, but they don't represent magnitude, they're just categories. All right, so we also talk about the levels or scales of measurement. And if you know French, this word means black, noir, but we also use this as an acronym, N-O-I-R, N-O-I-R, to remember the levels of measurement. You may have heard of film noir, 1940s thrillers. It's just a way to remember what the levels of measurement are. Again, nominal is the same as categorical. For example, gender, race, ethnicity, region, whatever that we want to use as categories. Ordinal implies an order, so birth order or Yelp review, but the deal about ordinal is that there's no fixed amount between the points in the order. So you could be the first child and the second child, but the distance between the first and the second child is different for each family, as well as the difference between your 1-star review and my 2-star review. We may have the same exact opinion about a particular restaurant, but you're just giving it a different label than I am. Interval is, I'm pointing here, this is the thermometer, where the 0 is just a placeholder. So in Fahrenheit or Celsius, when it's 0 degrees outside, it does not mean there's no temperature, it's just a placeholder. And ratio, the difference for that is that when you get off the scale, I couldn't make the arrow go over there, but if you get off the scale, there's no weight on the scale. You get back on it, it measures your weight. So the 0 has meaning, whereas in interval, it does not. In SPSS, we lump these two together and it's just called scale. Okay, so here's some examples of nominal, eye color, ordinal, ranks of colleges in the US News and World Report, interval, body temperatures in degrees Fahrenheit or Celsius, and ratio, heights, lengths, distances, volumes. So discrete data, a set of data is said to be discrete if the values belonging to the set are distinct and separate and unconnected. So number of births or deaths, you can't have a half of a live birth or half of a death. Number of patients seen, you can't see half of a patient. Number of people in this class, we have no fractional people. That's discrete data. Continuous data is a set of data is said to be continuous if the values belonging to the set can take on any value within a finite or infinite interval. So height of a patient, blood pressure, temperature. We have fractional values between heights. So those are continuous data. Big data and missing data, this is a new thing with our computing power. We're now able to examine extremely large data sets with the analysis required, large computer capability. Data science is the marriage of statistics, computer science, and software engineering in the context of a relevant field, such as epidemiology or biology. We're not going to cover big data in this class, but that's what it is. So clearly missing data means data that are missing, right? And discussions of missing data can get very complex because we can sometimes fill in our missing data with statistical procedures, but it's important to know why the data are missing. If they're missing at random and you remove those people, there are those observations from your data set, it's likely not going to change the findings of your data set or your analysis. But if the data aren't missing at random, then there's some underlying reason why they are missing, and it will impact your findings, because then your sample is no longer representative of the population from which it was drawn. For example, if you have a survey item that says, what is your income? And you have a group of people that answer everything else in your survey, but they don't answer that one. It's likely that the people who are either high wage earners or low wage earners are the ones who skip that question. And so, yeah, you could remove them, but then you no longer have rich people represented in your sample or poor people represented in your sample. All right, in this section, we're going to talk about sampling strategies and experimental designs. The randomized controlled trial is called the gold standard because they're the most effective. When you do an experiment, you apply a treatment and observe the effect on the individuals. You can also do observational studies where you observe and measure specific characteristics, but you don't attempt to modify the subjects. All right, so there are some characteristics of experiments. When you do an experiment, if you have the same effect with other samples and other settings, you have replicated the study, and if you see significant findings across different populations and different groups, then that's evidence that the effect that you found is a real effect. Blinding is when the subjects don't know if they're receiving the treatment or control, and if it's the subjects and the experimenters don't know that they're receiving the treatment or control. That's called the double blind. And you do that so that you can eliminate the placebo effect, which is even though you've gotten a placebo, it still produces an effect. And then randomization is used as a way to equate the groups when assigning the subjects to the treatment or control. So we randomly select from a population so that we can generalize the findings back to the population. And we also randomly assign to treatment or control so that we can say that when we started with our experiment, that those groups were as equal as they could possibly be. And it's because they were randomly assigned to the groups. So I'm going to talk about simple random samples. So when we randomly select from a population, if we do a simple random sample, it's simply that. We just pull names out of a hat, or we use a computer to randomize and select subjects to our treatment or control groups. Specifically, every possible sample of the same size n has the same chance of being chosen. There are other types of sampling. Systematic, which is you pull a number out of a hat, maybe from 1 to 10, say you pull 7, and then every 7th person is chosen. We have a convenience sample, that's just who the researcher has access to. We have stratified sampling, which is where the strata, i.e. gender, is representative of the population. So say we have a sample of nursing students, and perhaps it's 75% female, 25% male. We would want to pull from our population a sample that is 75-25. And then cluster, you divide the population into clusters and then randomly select the clusters from which all members would be sampled. And then here's just a graphic from the book, figure 1.3, simple random sample, systematic, convenient, stratified, and cluster sampling. There are many more sampling strategies, it's just a smattering of them. So for a visual, here's an example. We want a sample from the population to describe the picture below. If we randomly sample enough of the population, we can see a rough picture of the population. Right now I can see some of these pixels, but I can't make out the picture. If my sample is adequately large enough, I can see the beginnings of a face. If it's larger than that, I can see, yes, that's the picture of Einstein with his tongue sticking out. If I sample just a large enough group of individuals, I get the whole picture, but if I do clusters, I can see that I can't really quite make out what's going on there. If we have exclusions from the population, we eliminate potentially very important information. If I need to know if his mouth is open or closed, then I excluded 65 and older from my sample, I'm not going to know. Or whether his eyes are open, or whether he's wearing a tie. So exclusions from the population happen. It's okay, but it's going to limit your generalizability to the population from which you were drawn. Sampling error, or random sampling error, is when there is a discrepancy between the sample result and true population result. The non-sampling error is a result of human error, and non-random sampling error is not using a random sampling method. We have different types of experiments: cross-sectional, retrospective, and prospective. And in a cross-sectional study, data are observed, measured, and collected at one point in time. In a retrospective, we can have a case-controlled are retrospective, but they can also be retrospective. You can also have a retrospective cohort study, which I'll get to in a few more slides. But these are data that are collected from a past time period by going back in time, record review. We do a lot of those in medical studies. Prospective or longitudinal or cohort study. A prospective cohort study are data that are collected into the future from groups, cohorts that share a common factor, i.e. those that are at risk for myocardial infarction. All right, real quick, I want to acknowledge that this graphic is on page 28, but it doesn't have enough information, so I'm going to give you a different graphic. Case control studies are always retrospective. We start in the present. We know how many people have the outcome or do not have the outcome, and we look into the past at the proportion of defined exposure. We don't know anything about the future, okay? We clearly define our two groups at the start, one with the disease and one without, or with the outcome of interest. It could be teen drinking, teen pregnancy, whatever. Looking back to assess significant differences in rates of exposure to a risk factor, and the main outcome measure in case control studies is an odds ratio. You cannot draw causation from these types of studies. Now I've removed this future here because I want to just add this example. Say, for example, we're looking at 200 kids with cancer versus 200 kids without cancer. We already know who has cancer in the present, right? And we know that there's 50% rate in this study because we set it up that way, 200 and 200. But that's not the prevalence of cancer, childhood cancer in the population. We set our study up this way, which is why we use odds ratios and not relative risk, which I'll cover in a couple of weeks. Okay. Retrospective cohort studies are not as common as prospective cohort studies, and they're not the same as case control studies. Exposures are defined before looking at existing outcome data to see whether exposure to a risk factor is significantly different in the outcome development rate. And that's all I'll say about it for now. Prospective cohort studies clearly define two groups at the start, regardless of exposure or outcome. I ran out of space on my slide, but there's nothing happening in the past. We start in the present and we move forward with a cohort. The study then follows the participants for a defined period to see who develops the outcome or disease of interest. Cohort studies are good for assessing prognosis, risk factors, and harm. Outcome measure is risk ratio or relative risk. And we'll talk about that again in the future. Okay, so we have some other things about experiments that I want to mention. Confounding is when there's an obvious effect, but we can't identify the specific cause. And this can be alleviated by using the following designs. Completely randomized experimental designs are RCT, randomized control trial. Use random selection and random assignment to treatment or control groups. That's the gold standard. We can use randomized block design, formed blocks of subjects with similar characteristics and randomly assigned to treatment or control within each block. Say, for example, we block cholesterol study on gender, right? And then we can do a matched pairs design. We can look at before, after, measurements before and after some sort of treatment, or we could do something like a twin study where one twin is in a treatment group and the other is in the control group. Okay, we've talked about a lot of things. So to sum it up, we talked about discrete versus continuous data. We looked at parameter versus statistic. We looked at the levels of measurement, nominal, which is a naming variable, order, ordinal, interval, no real zero. Zero is just a placeholder. And ratio, where zero means lack of something or absence of something. We talked about different sampling techniques, simple, systematic, stratified, convenience, and cluster. We talked about types of studies, completely randomized, randomized block design, matched pairs, and confounding. And we also talked about cohort, retrospective, and prospective studies, and case control studies. All right.